Welcome to DAR Tutors for online and home tuition. Today, we begin our study of IB Chemistry Higher Level by exploring section S1.1, Models of the Particulate Nature of Matter. Our guiding question throughout this topic will be, how can we model the particulate nature of matter? We will address this by focusing on 4 key learning objectives. First, you will learn to distinguish between elements, compounds, and mixtures. Second, you will be able to describe the 3 states of matter. Third, you will understand how to convert temperatures between the Celsius and Kelvin scales. And finally, you will learn to interpret heating and cooling curves. By the end of this video, you will have a solid foundation in these fundamental concepts of matter. Let's begin with the basics. Chemistry is defined as the study of matter and its reactions. Matter is anything that has mass and occupies space or volume. It's the stuff that makes up our entire universe. Crucially, matter is composed of tiny, discrete particles. These can be atoms, ions, or molecules. We can think about matter in 3 ways: macroscopic, microscopic, and symbolic. The macroscopic level is what we can see, touch, and measure directly in a lab. It deals with the bulk properties like color, density, or whether a substance is a solid, liquid, or gas. The microscopic or particle level is how we interpret these macroscopic observations. It describes the behavior and interactions of the individual atoms and molecules that we cannot see directly. The symbolic level provides a shorthand to describe the macroscopic and microscopic. This is where we use chemical formulas, equations, and diagrams to represent chemical phenomena. This triangle is a core principle in chemistry. Chemists think at the particle level to explain their experiments at the macroscopic level, and then represent their findings symbolically. Based on these levels, we can classify matter. The broadest classification is into pure substances and mixtures. Pure substances have a fixed composition and distinct constant properties, like a fixed melting point. Mixtures, on the other hand, have a variable composition, meaning the ratio of components can change. Their properties are the sum of their components, and they typically melt or boil over a range of temperatures. A key difference is that pure substances cannot be separated by physical methods, only chemical ones. Mixtures, however, can be separated physically. Pure substances are further divided into elements and compounds. An element is a substance made of only one type of atom. It's the simplest chemical building block and cannot be broken down into simpler substances by any chemical change. A single atom is the smallest particle of an element that can exist. A compound is formed when 2 or more different elements are bonded together chemically in a fixed ratio. Unlike a mixture, a compound forms new substances with properties completely different from its constituent elements. A great example is the reaction of hydrogen and oxygen to form water. Hydrogen is a gas at room temperature and pressure. Oxygen is a gas, and both are highly flammable. But when they combine in a 2-to-1 ratio to form the compound water, we get a liquid that is essential for life and used to put out fires. The properties have completely changed. So, how are elements organized and identified? They are all listed on the periodic table. Each box on the periodic table represents a unique element. It contains the element's chemical symbol, which is always 1 or 2 letters, with the first letter capitalized. It also shows the atomic number, which represents the number of protons and uniquely identifies the element, and the relative atomic mass. Elements can be atoms, like neon. But many nonmetal elements exist as molecules, where 2 or more atoms of the same element are bonded together covalently. These are called molecular elements. The most common are the 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, which are all found as molecules of 2 atoms. There are also polyatomic elements like sulfur, which exists as S8 ring structures, and phosphorus as P4 tetrahedra. An important concept related to elements is allotropy. This is when an element can exist in different structural forms, which have different physical properties. For example, the element carbon can exist as diamond, graphite, or fullerenes, all with distinct properties. Oxygen has 2 allotropes: dioxygen, or O2, the oxygen we breathe, and trioxygen, or O3, which is better known as ozone. Let's apply our knowledge of classifying matter to a worked example. We need to identify whether the particles in these diagrams represent an element, a compound, or a mixture. Let's look at diagram A. we see several particles that are all identical. This represents a single element in its atomic form. Remember, an element is defined by having only one type of atom, and these are clearly identical. Now consider diagram B. Here we see two different types of particles: single, unbonded spheres, and diatomic molecules. Since there are different types of particles mixed together but not chemically bonded to each other, this is a mixture of two elements. In diagram E, all the particles are identical molecules, and each molecule is made up of two different types of atoms chemically bonded together. Because we have two different elements bonded in a fixed ratio, and all the particles are the same, this is a compound. Finally, let's look at diagram F. This diagram shows a mixture of two different substances, a diatomic element and a compound. There are molecules composed of two identical atoms, and there are molecules composed of two different atoms. Because we have multiple distinct substances mixed together but not bonded to one another, this is a mixture. Mixtures themselves can be further classified based on the uniformity of their composition. This leads us to homogeneous mixtures and heterogeneous mixtures. A homogeneous mixture has a uniform composition throughout. You cannot distinguish its components with the naked eye. Examples include air, which is a mixture of gases like nitrogen and oxygen, or salt dissolved in water, which forms a uniform solution. A heterogeneous mixture does not have a uniform composition. You can see the distinct components or phases. Sand mixed with water is a classic example. You can see the grains of sand separate from the water. Blood is also a heterogeneous mixture, composed of a liquid plasma and various blood cells suspended within it. This brings us to a key application of mixtures: separation. If we have a mixture of substances, we often need to separate them into their pure components for analysis or use. The choice of separation technique depends on the physical properties of the substances we want to separate. We can separate solids from liquids using filtration if the solid is insoluble, or evaporation crystallization if it's soluble. For immiscible liquids, like oil and water, a separating funnel is used. For miscible liquids, like ethanol and water, we rely on differences in boiling point, using fractional distillation. Another powerful technique for separating complex mixtures of soluble substances, such as pigments in plant leaves, is chromatography, which separates components based on their different interactions with a stationary and mobile phase. Let's work through an example of how to plan a separation. Suppose you have a skin ointment and you need to isolate the pure hydrocarbon camphor from it. Your lab analysis shows the sample is contaminated with table salt or sodium chloride and rust, which is hydrated iron oxide. We need to find a way to remove the salt and rust, leaving pure camphor. To do this, we need to consider the physical properties of our three substances. Table salt is an ionic compound and is soluble in water. Rust is a metal oxide and is insoluble in water. Camphor is a nonpolar hydrocarbon and is insoluble in water, but it is soluble in ethanol. Now we can design a two-step process. Step 1. We add ethanol to the impure mixture. This will dissolve the camphor but will leave the salt and rust as solids. They will not dissolve in the ethanol. The mixture now consists of a liquid ethanol camphor solution with solid salt and rust suspended in it. Step 2. To separate the liquid from the solids, we can use filtration. We pour the mixture through a piece of filter paper in a funnel. The ethanol camphor solution will pass through as the filtrate, while the solid salt and rust will be left behind on the filter paper as the residue. Now we have a clean solution of camphor and ethanol. To get the pure camphor solid, we simply evaporate the ethanol. We can do this by heating it gently in a water bath to remove all the solvent, leaving the pure, solid camphor behind. This is a practical method to purify the substance. Let's pause our exploration of matter to acknowledge our sponsor. This video is brought to you by DAR Tutors. If you need expert tuition in IB chemistry or any other IB A-level or IGCSE subject, DAR Tutors offers personalized online and home tuition. Visit their website or contact them today to find a tutor who can help you achieve your academic goals. We've classified matter by its composition. Now let's classify it by its physical state. This leads us to the three states of matter. The states of matter are solids, liquids, and gases. The key to understanding the properties of each state is the kinetic molecular theory. This theory states that all matter is made of particles that are in constant random motion. The state of matter a substance is in depends on two main factors: the distances between the particles and the forces of attraction between them. In a solid, the particles are very close together, often in a regular repeating lattice. The forces of attraction are strong, holding the particles in fixed positions. They can only vibrate, giving a solid a fixed shape and a fixed volume. Because they are already so tightly packed, solids are virtually incompressible. In a liquid, the particles are still close, but they are arranged randomly. The forces of attraction are weaker than in a solid, allowing particles to slide past each other. This gives a liquid a fixed volume but a shape that takes the form of its container. Like solids, liquids are difficult to compress because their particles are still in close contact. In a gas, the particles are very far apart. The forces of attraction between them are negligible, except during very brief collisions. Gas particles move randomly at high speed. This means a gas has neither a fixed shape nor a fixed volume, and it will fill any container. The large spaces between particles make gases highly compressible. We represent the state of matter using state symbols and chemical equations. S for solid, L for liquid, G for gas, and AQ for an aqueous solution where the substance is dissolved in water. We can see the states of matter in action through changes of state. This diagram summarizes the key changes of state and whether they involve heating or cooling. The process of a substance changing state is a physical change, not a chemical change. This is a very important point. For example, ice, liquid water, and steam are all made of H2O molecules. The only difference is the arrangement and energy of the molecules. During a change of state, the temperature of the substance remains constant. The heat being supplied or removed is not used to increase the kinetic energy of the particles, which would cause a temperature change. Instead, it is used to increase or decrease the potential energy of the particles by breaking or forming the attractive forces between them. For example, when ice at 0 degrees Celsius melts to become liquid water, the temperature stays at 0 degrees. The heat supplied provides the energy to overcome the hydrogen bonds holding the water molecules in their fixed positions, allowing them to move more freely. This heat energy is known as latent heat. A heating curve, which plots temperature versus time, clearly illustrates this phenomenon with flat horizontal regions at the melting and boiling points, known as plateaus. Let's work through an example to interpret these curves. This data shows the cooling of dodecanoic acid. A cooling curve plots temperature on the y-axis against time on the x-axis. As the liquid cools, its temperature decreases. But at 44.0 degrees Celsius, a plateau appears, where the temperature remains constant for about 3 minutes. This constant temperature period is the freezing point of the substance. During this time, the liquid is transforming into a solid. After all the liquid has solidified, the solid continues to cool. Therefore, the freezing point of dodecanoic acid is 44.0 degrees Celsius. Understanding temperature is crucial for the kinetic molecular theory. Temperature is a measure of the average kinetic energy of the particles in a substance. When you heat a substance, you increase the kinetic energy of its particles, causing them to move faster. A common point of confusion is the difference between heat and temperature. Temperature is the average kinetic energy, while heat is the transfer of thermal energy from a hotter object to a colder one. The mass of a substance is also important. Consider 2 beakers of water, a small one and a large one, both at 25 degrees Celsius. They have the same temperature. But the large beaker has more H2O molecules in it, so the total energy stored in all its particles, called its internal energy, is much greater. If we transfer the same amount of heat energy to both beakers, the small beaker will experience a much larger temperature increase because the heat energy is distributed among fewer particles, resulting in a higher average kinetic energy per particle. Finally, we need to be familiar with the 2 main temperature scales in chemistry. First, the Celsius scale, which you are likely already familiar with. On this scale, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Second, the Kelvin scale, which is the absolute or thermodynamic temperature scale and the SI unit for temperature. Water freezes at 273.15 Kelvin and boils at 373.15 Kelvin. The Kelvin scale is based on absolute zero, the theoretical lowest possible temperature where particle motion stops. This is 0 Kelvin or 273.15 degrees Celsius. An important point is that temperature in Kelvin is directly proportional to the average kinetic energy of particles. To convert from Celsius to Kelvin, you simply add 273.15. To go from Kelvin to Celsius, you subtract 273.15. Notice that because the size of 1 degree Celsius is the same as 1 Kelvin, a change in temperature has the same numerical value on both scales. For example, a 10 degrees Celsius rise is also a 10 Kelvin rise. Now let's practice with some IB-style questions. Here is our first practice question. Take a moment to read it and try to answer it on your own before I reveal the solution. Let's analyze the options. A mixture contains at least two types of particles. A diatomic element contains molecules, which are a specific type of particle. A compound, like water, contains only one type of molecule. Therefore, only a pure sample of a compound, such as pure H2O, will contain only one type of particle, the water molecule. Here is practice question 2. Again, pause the video and think about your answer. Remember our discussion on changes of state. During a phase change, the temperature remains constant. The plateau on a heating curve represents the temperature at which the solid is melting into a liquid. This temperature is known as the melting point. Question 3. How would you separate the components of this mixture? Let's break this down. First, the mixture is heterogeneous because sand is insoluble. We can easily separate the solid sand from the liquid solution of water and dye by filtration. Filtration removes the sand as a residue. Now we are left with the filtrate, which is the homogeneous solution of the colored dye in water. Since the dye is colored, it is likely a mixture of different pigments. To find out or to separate these different components, we would use chromatography. Question 4. Tests your knowledge of temperature conversions. Remember the top tip we learned. A change in temperature has the same numerical value on both the Celsius and Kelvin scales. Therefore, a 15 degrees Celsius increase is equivalent to a 15 Kelvin increase. There is no need to add or subtract 273.15, as that is only for converting a specific temperature from one scale to the other, not for a temperature change. Our final question for today. Let's review the options. Liquids do not have a fixed shape, so A is incorrect. Liquids are not easily compressible, so B is incorrect. Gas particles move randomly at high speeds, not liquid particles, so C is incorrect. In a liquid, particles are in constant random motion, but they remain close to one another, which correctly describes the liquid state. Let's quickly recap what we've covered today. We started by classifying matter into pure substances like elements and compounds and mixtures. We saw that pure substances have fixed properties and cannot be physically separated, while mixtures have variable properties and can. We also distinguished between homogeneous and heterogeneous mixtures and discussed how physical properties are used to separate their components. Next, we used the kinetic molecular theory to explain the properties of solids, liquids, and gases, focusing on interparticle distances and forces. We analyzed heating and cooling curves, understanding that the plateaus represent changes of state occurring at constant temperature, and we practiced converting between Celsius and Kelvin. These concepts form the cornerstone of your IB chemistry journey. Mastering them will make many future topics much clearer. Thank you for watching this DAR Tutors video. For more expert-led lessons and personalized support in your IB chemistry studies, please visit our website and contact DAR Tutors.